In this video, we're going to increase the complexity of our modeling of power flow by adding transmission lines into our model. We'll also talk about representing power on a log scale. I've drawn the circuit we'll be considering here. It's the same as the circuit we used to prove the maximum power transfer theorem, but we've added a transmission line between the source and the load, and we replaced ZS with a purely real impedance matched to the line. We'll take a look at what happens when ZS isn't matched in a later video, but for now, that degree of freedom would add complexity without adding much understanding. We're going to calculate power delivered to the load in two different ways to show that, one, the two ways are the same, so you can use either tool, and two, the second way is pretty quick. We know power in the load is going to be given by the complex conjugate of V times I, and we can represent those values in terms of gamma and the wave amplitude, which is 1/2 of the generator amplitude, because our source is matched. So we get VZP over 2 here instead of VZP because of the divider between Z0 and the driving point impedance of our line. Recall that the voltage at the load is given by the sum of waves, so it's proportional to 1 plus gamma, which is conjugated because our voltage is conjugated. And the current at the load is given by the difference between our incident and reflected waves, so it's proportional to 1 minus gamma. Also, we find the current by dividing our expression for voltage by Z0 here. We can factor out VZP in the factors of 2 to get a distinctive coefficient, which is VZP squared over 8Z0. This coefficient is all over power calculations, so it's comforting when you see it. Notice that the factor of 8 comes from 3 factors of 2. 1 because we're finding the average power when we're driven by a sinusoid, and 2 because the amplitude of the forward-going wave is half of the generator voltage. We've also expressed gamma in its complex exponential form, which has let us take the complex conjugate pretty easily. The multiplication of these two gamma terms leaves us with 1 minus the magnitude of gamma squared. This is an intuitive result. High reflection coefficients should reduce the amount of power in the load. We're going to hone that intuition further by deriving this same result from conservation of power in the system. Leaning on power conservation requires us to remember how much power is in a wave. Fortunately, we defined A to have an easy relation to power. Specifically, power is 1/2 of the magnitude of A squared. A was defined as the right traveling amplitude squared over 2Z0, which is equal to VZP squared over 8Z0 in this case. Power conservation states that any power carried into the load by wave A needs to either be dissipated or reflected out on wave B. And we can express how much power is reflected in terms of the reflection coefficient. We know B is gamma times A because gamma is defined as V minus over V plus. And if you multiply both sides of that equation by their complex conjugate, you can find an expression for the magnitude of B squared. That value is the reflected power, and it's directly dependent on gamma. Rearranging our conservation equation, we find that the power in the load has to be the incident power multiplied by 1 minus the magnitude of the gamma squared. And substituting for incident power, we find the same result we had in the left column. However, by using the magnitude of gamma squared as a kind of power gain, we were able to skip all the complex math. That's handy here, and it's really handy when working with measured quantities in lab, as we'll see on the next slide. In the spirit of this video set, we're going to try calculating the power dissipated in the 150 ohm in this example in 2 different ways. We'll try doing normal multiplying and adding first, and then we're going to see if we can go even faster using logarithms. The power in our incident wave is 1/2 of the magnitude of A squared, which we find to be 1/4 of a milliwatt. As an aside, I find it handy to remember that the leading factor of 1/2 and the 1 over Z0 factor combine to a factor of 1 over 100 in 50 ohm systems. So you're just dividing your amplitude squared by 100. Gamma is 0.5 for this example. So the reflected power is going to be 1/4 of a milliwatt times 0.5 squared, which is 1/16 of a milliwatt. The rest of the power goes into the load, so it receives 3/16 of a milliwatt. Fine, that seemed easy enough, but it can get kind of tough to carry power levels that are minute fractions of a milliwatt around in our head. So we're going to try this again with logarithms. The power in this incident wave is minus 6 dBm. That's a unit you might not have used a lot, but it means decibels relative to a milliwatt. And because decibels are defined by 10 times the log of a ratio of powers, you can think of it using the expression I've just written on the right. I didn't actually use that expression to calculate this value though. I just remembered that minus 3 dB corresponds to a factor of 1/2 in power, and we had 2 of those from our expression for wave power on the left. So I started at 1 dBm, which is 1 milliwatt, and noticing that we divide by 2 twice, I subtracted 3 dB for each of those. Rather than finding the reflection coefficient for this approach, we're going to find a quantity called the return loss. This is the ratio of reflected power to incident power expressed in decibels. And note that because power is proportional to gamma squared, we're using 20 log in this expression rather than the 10 log we use for power quantities. Logs are great because we can turn tricky multiplications into addition. We know the incident power is minus 6 dBm, and we add our return loss to that to find that our reflected power is minus 12 dBm. That was super easy to do in our head. The decibels and power gains remain popular in practice because you can add these log quantities in your head rather than having to multiply. In case you can't do the conversion right offhand, 10 raised to the minus 12 over 10 is 0.063. So this answer gives us the same result as the left column. However, logs have a downfall. You can't just find the difference between minus 6 dBm and minus 12 dBm to determine how much power is in the load because logs don't add that way. You have to convert your results back to linear quantities to use conservation relationships. One final note, definitions of return loss are inconsistent, and it's sometimes defined as a positive quantity that you have to subtract from your incident power. This is fine, and it's easy to convert between the definitions by remembering that your reflected signal should probably wind up smaller than your incident signal. Just make sure to read context clues when you're dealing with return loss. So in summary, wave power conservation is an easy way to calculate load power. Return loss is the reflection coefficient expressed in decibels. And power gains in decibels make it easy to find power levels in your head.